Hey everybody, welcome to Math 35. This is college algebra at College of the Sequoias, and this is the beginning of the entire semester. We're going to start with some review. Some of this terminology you may have never seen because it's a lot of math jargon, but you need to have at least seen it and know a little bit about what it is. So we're going to start off, it's called Chapter R for Chapter Review, and this is section R1. So R1, and that is on set notation. The rest of the semester, and most mathematicians use set notation to describe collections of numbers and things like that. And so it's handy to just get some terminology out of the way. So a set, let's just start off with that is a collection of objects. And objects in the set are called elements. Or members. They say members of the set. And what we do is we use curly braces that look like that to identify our sets. Where the elements are inside of it. Inside the braces. Okay, it's important to note order does not matter. So if we look at the numbers 1, 2, 3, as we call that a set of numbers, we could say 1, 2, 3, that's one set. But I can also describe that as 3, 2, 1, or I could say 2, 1, 3. Any of those setups will work. The order is not important. And so that's how we write sets. If we want to show something as an element of a set, so depicting an element of a set, we use this. It's a funky looking E, capital E. It's more like a C with a horizontal line in it. And we'll say like 3 is an element of 1, 2, 3. And then if we want not an element, we're just gonna put the little cross out symbol, like the Ghostbusters sign. So 4 is not an element of 1, 2, 3. Okay. Pause, leave that up for a second so you can finish writing. You might pause it so you can do so. Okay. We often give sets names, and a lot of times it's a capital letter. So we could say the set S, we're going to call that 1, 2, 3, 4, 5. And if the number of elements is countable, and it can be a big number, but still countable, we say the set is finite. which means that there's a start and an end. There's only so many. There's a limited number of elements. Now, if it keeps going on forever and ever, like our number system does, if we have unlimited number of elements, we say that's an infinite set. And I know, I assume everyone's heard the word infinity, to infinity and beyond, you know, good old Toy Story. Infinite just means unending. It's unending. I don't know why we say finite and we don't say infinite. You would think that would be how we say it, but we say finite or infinite. So the way you pronounce them is different, but one means limited number and the other means unlimited number. So examples of unlimited sets or infinite sets, we have the set n. N is natural numbers. And you know these numbers, they're 1, 2, 3, 4, and they just keep going. And this little, where you put 3 dots in a row like that, those are called the ellipses, which is funny because near the end of this semester, we're going to have a different thing for ellipses. But what that means is just keep repeating the pattern continuously. Keep the pattern and repeat continuously. So the pattern here is add 1 to the previous element. So we add 1 to 4, the next one's 5. We add 1 to 5, the next one's 6. You guys know this kind of stuff. So those are sets. We have something called set builder notation. This is a lot of math jargon, and I'm not going to use it that often, but the homework will. And the way set builder notation works is something like this. They'll have something like this, F equals, and then they'll do curly braces. They'll say X. There will be a vertical line, and then it'll give a description. X is a fraction between 0 and 1. And then they'll end the curly braces. The way this is read, this first X means the set of all elements X. This vertical line means such that. And this part here means exactly what it says. So F is the set of all elements X such that X is a fraction between 0 and 1. So this includes X is any number like 1/2 or 1/3 or 1/4 or 2/5, 7/9, any fraction that is less than 1 but greater than 0. So that's the notation they'll use. It'll show up. The vertical bar is just like the divider. It means everything that after the vertical bar is what's in the set, and what comes before the bar is what the set is made up of. All right, I'll pause for a second. I recommend pausing and writing down what you need. Okay, we start our next one. We've got some other sets. U, the set U. I'm going to put a tail on it. It's a capital U, though. This is called the universal set. And the universal set contains all the elements that are appropriate to a given situation, problem, or environment. I'm having problems writing this morning. I have not had enough coffee. Environment. Let's try that again. Environment. Okay. So this makes me sad, but I know this is the case. Not everyone knows what a deck of playing cards is, but I can pull out a set of cards and show you real quick. If you've never used them, a set of playing cards, there's 52 of them. They go for 8, they go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then they have a jack, which is a J, it goes by J. Where's my J? The jack, the queen, the king. The numbers 2 through 10 show their numbers. The 1 is called the ace, and everything else is the same. They have 4 shapes on them as well. This thing that looks like a black heart with a stem sticking out, it's called a spade. I assume everyone knows what a heart is. Everyone knows what a diamond is. And these are called the clubs. They look like 3-leaf clovers. So there's 4 suits. These are called suits, and there's 13 cards in each suit. There's 52 cards. If I wanted to talk about the universal set of cards, I could say for like a deck of playing cards, I could list each card in the set. U is ace of spades, king of spades, dot, 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 all in, and go through all 52 cards. So we can have the universal set isn't just numbers. It can be anything. That's why I'm showing this. It can be anything. Let me put these cards away. If a set is completely empty, if there's nothing in the set, a completely empty set is called that. It's called 2 things. It's either called the empty set or null set. It has no elements. The set has no elements. And we tend to write it 2 ways. Option A is valid. We use curly braces, nothing inside. You'll also see people do a 0 with a bar through it. This can be confused for 0. So it's better off to use the top one, because a lot of times people put that bar through 0 to make sure it's not make it clear it's not a capital O. So that can be confusing, and the empty braces is the one to do. We do never use the braces with that inside. That's going to tell people that 0 is in the set and 0 is the only number in the set. Even though in our world, and when we're counting things, 0 is the absence of something. In mathematics, 0 is a valid number. It's a number. It's not missing. So its description in math and the way we use it when we're counting things are a little bit different. So never put the 0 inside the braces, just use the empty braces. I'll pause for a second, let you deal with this one. All right. So if we want to show something is inside, one set is inside of another, one set inside another is called a subset. If we have the set S is 1, 2, 3, 4, 5, and we stop, and N is our natural numbers, again, recall that's 1, 2, 3, and we keep going. S is a subset of N. And the way we depict subsets in mathematics is we use the symbol. It looks like a little bit like a flattened C with a line underneath it. So S is a subset of N. If we do it the other way, N does not go inside of S. So we would say N is not a subset of S. So this means subset. And a bar through it means not a subset. The null set is a subset of every set. So is a subset of N. Another interesting thing, okay, so using that kind of idea, if every element of A is an element of B, so A is a subset of B, and every element of B is an element in A, so B is a subset of A, this only works if the sets A and B equal. They're identical. Okay. All right. Next topic, Venn diagrams. Again, remember to pause if you need pauses in here. We're not doing a lot of mathematics right now, even for like a couple sections, but we're getting some terminology out of the way. Next thing we'll take a look at is Venn diagrams. My pen gets ahead of my brain. Venn diagrams. We draw them using a box. The big box is always our universal set, U. So U is our universal. Let's say we're talking about numbers. n is a subset of the universal, so we've got our natural numbers. We're going to draw a circle inside of u, call this n. And we had s was 1, 2, 3, 4, 5. That's part of n, that's inside of n, so we can put like s inside of n. And what this pictorially is showing that s is a subset of n, and n is a subset of u. They're completely inside. Okay? Now I'm going to do it again. I'll draw that picture with our u. Our big box is u. I'm going to put u on the outside, though. This is u. We had our set of natural numbers on the inside. There are other numbers that are not natural numbers, like 1.5 is not a whole number. There's a decimal in there. I could say those are the natural numbers, and if I use n apostrophe for everything else, this makes up the other things. We say, the way I wrote this, n was natural numbers. And we put n with apostrophe is every other number that is not a natural number. This includes things like pi with circles. I'm sure you've heard of it. We've got negative numbers. Even 0 is not a natural number. And that little apostrophe, we say that a couple ways. We'll say n prime. Sometimes you'll see it written as this, n with a c instead. That's an alternative form, and it's a little bit clearer because the apostrophe is used in mathematics and calculus later on for derivatives. And the reason why they chose the C is the C stands for complement. And it's not like paying someone a compliment. It's spelled a little bit differently. So C means complement. NC is the complement of N. And the way it really works is if we took all the numbers n and we add all the numbers in its complement, we should get every number that exists. So that's the idea here. If we use our set builder notation, good times, I could say n prime or n complement is the number. We'll say x, the set of all elements x, such that x is in n, or x, I'm sorry, x is in u. There we go. X is u, but x is not in n. That's a little confusing, huh? I agree. But that's the terminology we have. We got some other things. Let's show some other notations. Again, please pause if you need this a little longer. I hope you're taking notes. I strongly encourage you to take notes. Watching me do this and you writing it out yourself are drastically different outcomes. So I'm going to use a couple different sets so that I can give an explanation. Let's say the set A is 1, 2, 3, 4. And we're going to say B is the sets 3, 4, 5, 6. Notice that A and B have some overlap. And when we have overlap, we call that intersection. When we want to use a symbol for intersection, we use an upside down capital U. And the way this would work is I would say the set A intersects with the set B with the numbers 3 and 4. Those are the only overlapping numbers. So another way to put it, it's the intersection has elements that are common to both sets. I'm going to introduce you to a couple more cool math symbols. They're just shortcuts for writing out things that mathematicians end up saying a lot. They look like things you know. That capital A we have, so these are cool math symbols. I think they're cool because we use them for abbreviations and they look familiar. Cool math symbols. If I flip that capital A upside down, that means for all. Mathematicians use that enough in proofs and stuff like that that they say for all. And we will use a backwards capital E to say there exists. This is fancy math terminology. Okay, those are some cool math symbols. I just want to throw them in because I'm going to be using them. If I want to do a Venn diagram, try to pause this video and try to make a Venn diagram showing how A and B would look on the Venn diagram, and notice that they overlap. So maybe their pictures should overlap. I'll assume you hit pause and did it. I'm going to show it like this. We've got our universal numbers. I've got the set A. I've got the set B. A has 1 and 2, 3 and 4. So those are all in A's circle. And B has 3 and 4 and 5 and 6. So those are all in B's circle. So this region right here is A intersecting B. Let's look at some more terminology. Let's call the following sets this. Let's say O equals all the odd numbers, and E is the even numbers. The way they show the even numbers in set notation, they say even numbers are the numbers x, all elements x, such that x divided by 2 is a natural number. That's a lot of math jargon for even numbers, right? Notice though, the odd numbers and even numbers, they have nothing in common. And when this happens, we call these our disjoint sets. Disjoint sets. Two sets with nothing in common. Okay, pause for a second, and let's go back to the card example. I want to use cards again. It's a good way to describe the next thing. let's say this is a poker reference. So you have the 4 of diamonds, the 4, the 5, the 6, and 7 of diamonds. A 3 will give you a straight. A straight in poker is 5 numbers in a row, so 3, 4, 5, 6, 7, as will an 8. That's for a 5th card. You get 5 cards. If you get a 5th card, it's 8. Those will make straights. 3, 4, 5, 6, 7, or 5, 6, 7, 8. Another good card for you is another diamond. Another diamond, any diamond, will give you 5 diamonds, is called a flush. Five cards of the same suit is called a flush. And then if you get the 3 of diamonds, I'm going to list it like that, or 8 of diamonds, now you have 5 cards in a row that are the same suit. This would give you a straight flush. And that's 5 cards in a row, all the same suit. So let's say S is equal to 3 or 8. And we're going to say D is one of the remaining diamonds. One of the remaining diamonds. So either of these cards will work. And any other diamond or any other spade will give you a good hand. Any diamond or spade will give you a good hand. I'm not sorry, any diamond or 3-8 will give you a good hand. Good poker hand. So we want either one of those cards. If either set works, we use union. And that's depicted by a capital U, no tail on it, just a capital U like that. So we would say for this, both diamonds and the cards 3 or 8 are good for us. So D union S is any diamond three or 8. Okay. There is some intersection between the 3 and the 8. 3, 8, and the diamonds, and we actually wrote them up above. The 3 of diamonds or the 8 of diamonds give you a straight flush. So the intersection of D and S is the 3 of diamonds or the 8 of diamonds. Now, I should have did this better and used red ink for the diamond things, because diamonds are red in cards. Finally, I'll put up a Venn diagram of this last combination. So U is our universal set of cards, all 52 cards. We've got diamonds in here. We have the numbers 3 or 8. And in the intersection is the 3 of diamonds and the 8 of diamonds. Sometimes they use shading. They'll do stuff like this to indicate what you want. So if I shade like both the D and the S, shade both the D and the S, the shaded region is what we want. It's showing both D and S and where they overlap. That is D union S. All right, that's it for R1. I'll stop this and we'll make R2 in just a second. It takes a little while for this to convert to a video, and then I need to upload it to YouTube, but peace. We're going to start doing some fun math. Well, some math in a little bit. And end video.